Okay, we've covered a bunch of different ways of building functions, and so let me finish this series of lectures with a slightly longer example that shows how we can use all these higher order functions to build code just by putting together all the bits and pieces that we've seen today. So here's an example of where the input is some string and we want to create a table in alphabetical order listing the word counts. There's 1 occurrence of clouds, 2 of hello, 1 of sky. And so if we reviewed this table just as a raw string, that's what it would look like with new line characters in it. So that's a specification of the input and the output for this example, word counting. And we're going to use a good number of the techniques we've seen so far in this series of lectures. So the way we're going to do it is to sort of start with the input and massage it step by step to get to the output. So the first one is something which will break it into words. So we split the list we start with into its words. So let's define the word count. The argument is a list of characters. Let's call it a string, S. I'm not going to put the type in just yet because I want to modify the type as I go along. I'm going to actually incrementally build up this definition. It's one of the nice things about type inference, that we don't have to put the type in from the beginning because the type may change as we develop our function. So the natural thing, the first thing we think of then is the function words, which will split our string into its individual words. So let's start by doing that. That's our first step of our transformation. Okay, so what next? What could we do next? We could sort that, for example, because we know we're going to put things in order. By sorting this list of words, we're going to cluster together all the similar words. So let's do that. Let's sort all the words. And I'm going to use my dollar here to avoid putting brackets around words S. So let's just compile that. Oh, we haven't got a sort function. That's not a standard. At least it's not. We don't get it for free. We need to import it. It's in data.list, and the function sort will do the job for us. So where were we? Okay. Let's do a word count on our verse, and what it's done is then sorted the words using the polymorphic sorting function. It can sort anything which is ordered, anything which you can compare when one thing is bigger than another. So for any ordered A, it can take a list of A's and give you back a sorted list of A's. Now what we want to do is kind of count these groups of words that appear one after the other. In this case, there are 2 A's. And in fact, there is a standard function that will do that, and that's called group. But actually, there's a higher order version of that called group by. And I didn't show this example, but here it is. Group by some predicate P breaks lists into segments where the adjacent elements in each segment satisfy the property. And group by are also in data.list. So let's import those and have a little play with those. Okay, so I'm just going to use regular group, which is the same as grouping by equality. It groups all the equal things together. Now there is actually I want to show you another way of avoiding brackets. One way to do it was to use this dollar operation. But another way to do it is to use something called function composition. Now, it's a notation that you may have seen before in mathematics. In mathematics, you write a little circle operator for function composition. In Haskell, you use a dot, which, I mean, in principle, you could use a circle because you can use Unicode characters, but the standard Haskell way is to use a dot. So just make sure you don't get confused when you see dot and you start thinking of field selection in object-oriented languages. Dot in Haskell is function composition. So what we can do is actually define this not using dollar, but using just pure functions. Word count we're going to build as a pipeline of composed functions. And so far we've composed 3 functions. We're not done yet. But we're going to do the words, then we sort those, and then we group those. Now you might find this looks a bit unnatural because we're kind of doing things backwards. That's the way function composition works. There are actually programming functional languages that have a more forward style, and they use a different operator. For example, F#, which is Microsoft's functional language. They would often write this function composition using a different operator, and they would write words, then sort, then group. You could actually easily define that thing yourselves, but we're going to do it in the standard Haskell style. So what does our function do so far? Well, what it does is cluster our words into groups of identical ones. And what we want to do now is, well, let's have a look at our slides to keep it in sync with what we were thinking of doing. So here's a suggestion for the next step. We're going to do a mapping function. For each list in this list of lists, we're going to combine the word with the number of the first element of the list with the number of things in that list. So it's a function that takes this list of words. So each one of the words in that is going to split it into a pair. So it's a list of strings, yes indeed. So each word in this list is identical. So we need to take any one of them, take the head. Will be non-empty because that's what group gives us. We take the head, which is one of the words, and the length of that list. So we'll get the first element of the pair will be the word. The second element will be the number of occurrences of that. Now I'm going to rearrange these down I'm going to write these vertically so that I've got room to keep expanding. And so what have we got so far? What does the code we've got so far do? It produces these pairs of words and counts. We're getting close to our final solution. What do we need to do next? Well, what we want to do next, let's massage this a little bit closer. We take each one of these pairs and we want to convert that into a table entry. And the way we're going to do that is just to combine the word and the count into a single string. We're going to join them together. So in order to join them together, we need to convert the number part into a string, and we use show to do that. So we're going to do another map operation. We're going to map, and we're going to take each pair. Now we can pattern match on that pair. And this is something we haven't seen before. When we use lambda notation, we can also combine it with pattern matching, and we can use a pattern. And here we're using a pattern of a word and the count. And we're going to append the word together with a colon and then a space. And then we're going to show the count. So that's the map operation that we're going to apply next. And let's call it n. N is a better word for a number. Better letter for a number. Okay, let's see what we've got now. We're getting pretty close. Yeah, we've got one occurrence of that, where mostly are just one occurrence of each word in this example, so it's not a great example text, but hopefully you get the point. Now to get to the last step, we just need to use a function we've seen before. It's the function which combines lines, single lines into one big line, and it's called unlines. And if I want to display it on the screen, I use putstra applied to that, and hopefully it will print it out nicely as a table. The highlighting looks a bit weird, but that's just the editor. So don't worry about the highlighting, but you notice there's only one of each word except for the word A.